Michael Faraday's journey from poverty to becoming one of the greatest scientists in history is one of the most remarkable stories of human potential, perseverance, and intellectual courage. To truly understand the significance of his rise, it is essential to look at the harsh environment into which he was born, the limited opportunities available to him, and the extraordinary determination that allowed him to transcend every barrier placed in his path. Faraday's life is not only a historical account of scientific achievement, but a powerful reminder that genius can emerge from the most unexpected places when passion and curiosity are allowed to flourish. His story begins in the early 19th century in London, a period defined by industrial change, rigid social classes, and widespread poverty. Faraday was born in 1791 to a poor family living in a small, cramped home in Newington Butts. His father, James Faraday, was a blacksmith who struggled with poor health his entire life, and the family survived on unstable and unpredictable earnings. The Faradays were part of the working class, a group that had almost no access to formal education, and in this environment, the idea of someone becoming a scientist, especially someone without wealth or social connections, was nearly impossible to imagine. Yet it is precisely this unlikely beginning that makes Faraday's accomplishments so extraordinary. Faraday received only the most basic schooling, enough to read, write, and perform simple arithmetic. He never attended university. He never studied Latin, which at the time was considered essential for scientific work, and he had no formal scientific mentors in his early years. Instead, he began working at the age of 13 as an errand boy for a local bookseller and binder named George Rebow. This job, which might have seemed insignificant to others, became the foundation for Faraday's intellectual awakening. While binding books, he was surrounded by volumes of science, philosophy, and mathematics knowledge he was never expected or encouraged to explore. But Faraday, driven by an intense internal curiosity, began reading everything he could get his hands on. He devoured books on electricity, chemistry, and the natural world. This informal education, self-directed and fueled entirely by passion, laid the groundwork for a scientific mind that would one day transform the modern world. During his time at the bookshop, Faraday began conducting simple experiments inspired by the books he read. He built crude electrical devices, tried basic chemical reactions, and copied out lecture notes to better understand the subjects that fascinated him. He made personal notebooks filled with diagrams, observations, and explanations, early signs of the meticulous experimentation and documentation that would later define his scientific career. What made Faraday remarkable was not just his curiosity, but his discipline. Unlike many young learners who explore knowledge superficially, Faraday approached science with seriousness and determination, treating it as a calling long before he had any opportunity to pursue it professionally. A turning point in Faraday's life came when a customer of the bookshop noticed his interest and gave him tickets to attend a series of lectures by the famous chemist Humphrey Davy at the Royal Institution. Davy was one of the most celebrated scientists of the time, known for his discoveries of several elements and his skill as a lecturer. Faraday attended these lectures with deep fascination, taking detailed notes and later binding them into a personal volume that he sent to Davy along with a request for employment. This was a bold move for a young man from Faraday's background, but it reflected his belief in the value of learning and his desire to contribute to the scientific world. Davy, impressed by Faraday's notes and recognizing his potential, eventually offered him a job as a laboratory assistant. This opportunity was life-changing. Faraday suddenly found himself in an environment filled with scientific instruments, experiments, and some of the greatest thinkers of his time. However, his entry into the scientific community was not easy. Many of the other assistants came from wealthier families and viewed Faraday as a mere servant. He was often asked to perform menial tasks unrelated to science, such as cleaning equipment or acting as a valet when Davy traveled. Despite this social pressure, Faraday remained focused on learning. Every moment in the laboratory was an opportunity for him to observe, ask questions, and absorb knowledge. Faraday's rise in the Royal Institution was slow but steady. His natural talent for experimentation became increasingly obvious as he contributed to research in chemistry, producing high-quality results and earning Davy's respect. Over time, he gained more responsibilities, conducting his own experiments and publishing scientific papers. His discoveries in chemistry, including the identification of benzene and improvements to the steel industry through better glassmaking, began to establish his reputation as a skilled scientist. Yet it was in the field of electricity and magnetism that Faraday would make his greatest impact. What makes his rise even more inspiring is that Faraday never allowed his lack of formal education to limit his vision. He approached scientific problems with fresh eyes, unburdened by academic traditions that sometimes constrained the thinking of more formally trained scientists. This allowed him to imagine possibilities that others might have dismissed. When he began investigating the relationship between electricity and magnetism, he did not rely on advanced mathematics, which he had never learned. Instead, he relied on intuition, experimentation, and physical reasoning. Faraday's notebooks from this period reveal a mind constantly questioning, testing, and refining ideas. His ability to visualize invisible forces, electric and magnetic fields, was revolutionary. In fact, the very concept of fields, which is central to modern physics, originated from Faraday's sketches and conceptual models. Faraday's discovery of electromagnetic induction in 1831 transformed science and technology. By demonstrating that motion through a magnetic field could produce an electric current, he unlocked the principle behind electric generators, a discovery that would eventually power entire cities. This achievement alone would have secured his place in history, but Faraday continued to expand knowledge through breakthroughs such as the laws of electrolysis and experiments leading to the understanding of diamagnetism. Each discovery was a testament to his ability to think independently and creatively, qualities that were rooted in his self-taught background. Despite his growing fame, Faraday remained humble and deeply grounded. He rejected honors that many scientists eagerly pursued, including knighthood, preferring to remain plain Michael Faraday. His character reflected his upbringing. He valued integrity, honesty, and service to society. Even at the height of his career, Faraday continued to deliver public lectures aimed at teaching science to ordinary people, including children. His famous Christmas lectures at the Royal Institution became a tradition that continues to this day, demonstrating that he never forgot the value of accessible education. These lectures were not only demonstrations of scientific principles, but celebrations of curiosity itself. Faraday's ability to communicate complex ideas in simple ways made him beloved by audiences far beyond the scientific community. Another remarkable aspect of Faraday's rise is his refusal to be constrained by the social norms of his time. The scientific world of the 19th century was dominated by wealthy men with university degrees and academic backgrounds. Faraday had none of these advantages, yet his contributions far exceeded those of many of his contemporaries. His story challenged the belief that scientific achievement was reserved only for the privileged. Through his work, Faraday demonstrated that passion, persistence, and creativity could overcome social class barriers. He showed that science was not an elite pursuit, but a universal human endeavor. Faraday's journey also highlights the importance of mentorship. While he was self-taught, he benefited enormously from the guidance and support of Humphrey Davy and the opportunities provided by the Royal Institution. This combination of self, motivation, and external support created the perfect environment for him to excel. His experience serves as a powerful example of how access to knowledge can transform a person's life, and it underscores the importance of providing educational opportunities to people from diverse backgrounds. As Faraday's scientific reputation grew, he eventually became one of the most respected and influential figures of his time. Universities and governments sought his advice. His experiments influenced not only physics and chemistry, but also engineering, communication, and industrial development. Yet he never distanced himself from his modest origins. His humility and dedication to learning remained constant throughout his life. He once said, "Nothing is too wonderful to be true if it be consistent with the laws of nature." This statement reflects both his philosophical outlook and his belief that discovery is accessible to anyone with the courage to explore. Faraday's life is often described as a story of a common man who achieved uncommon greatness, but this description does not fully capture the depth of his accomplishments. He did not simply rise from poverty, he reshaped the world. He did not merely become a successful scientist, he became a foundational figure whose work still defines modern technology. His contributions continue to influence everything from power generation to electronics to scientific teaching. Modern physics, including the work of James Clerk Maxwell and later Albert Einstein, built upon Faraday's insights. In fact, Einstein himself kept a picture of Faraday on the wall of his study, acknowledging the profound impact Faraday had on the development of scientific thought. Understanding Faraday's rise also means recognizing his resilience. He faced numerous obstacles, including social prejudice, lack of formal education, and even health challenges that later affected his ability to work. Yet he never stopped learning or questioning. His perseverance was driven not by the desire for fame or wealth, but by genuine curiosity and a deep belief in the value of scientific discovery. This inner motivation set him apart and allowed him to accomplish what few others could. In many ways, the story of Michael Faraday is a celebration of human potential. It shows that brilliance is not limited by birth, wealth, or formal credentials. It teaches that the greatest discoveries often come from those who think differently, challenge existing assumptions, and dare to imagine new possibilities. Faraday's rise from poverty to global recognition is not just a historical fact. It is a powerful narrative that continues to inspire scientists, students, and dreamers around the world. His life serves as a reminder that anyone, regardless of background, can contribute something extraordinary to the world if given the opportunity and driven by passion. Continuing the exploration of Michael Faraday's extraordinary rise, it becomes clear that his journey cannot be understood only through the lens of scientific achievement. It is also the story of a man who lived with profound humility, moral strength, and a dedication to public service that shaped his entire career. Faraday's transformation from a poor bookbinder's apprentice to one of the world's most respected scientists was not merely the result of talent. It was the product of his character, discipline, and unwavering belief in learning. His life demonstrates that greatness is not something one inherits, but something one builds step by step through curiosity and commitment. One of the most striking aspects of Faraday's journey is how he responded to success. Many people who achieve recognition early in life may become consumed by pride or self-importance, but Faraday's humility deepened as he matured. An upbringing in the Time Sandemanian Church, the Simpli, City, honesty, and modest living. The values he learned there became guiding principles throughout his life, shaping not only his personal behavior, but also his scientific approach. He viewed nature not as something to be conquered, but as something to be understood and respected. This view allowed him to pursue science with clarity and purpose, without the distractions of ego or ambition. Faraday's humility was also evident in the way he engaged with the scientific community. Despite his groundbreaking discoveries, he insisted that his work be evaluated on its own merit, not because of his personal reputation. When he found himself praised for major breakthroughs, he was known to deflect credit to the beauty of nature itself rather than his own brilliance. He once remarked, "I am no philosopher, but a simple man." Yet, this simplicity was deceptive. Behind it lay one of the most powerful scientific minds ever known. His modesty made his achievements even more remarkable, because it revealed that his motivation was never fame, only truth and understanding. Faraday's rise to global recognition was not confined to the world of science. He became an influential figure in politics, industry, and public education. His expertise was sought by the British government on matters ranging from lighthouse illumination to naval defense. One famous example was his role in helping develop a method to protect ships from corrosion by using electrical currents, a practical application of his research in electrochemistry. Faraday saw these responsibilities as opportunities to use science for the public good. He refused to exploit his knowledge for personal profit, turning down lucrative consulting offers because he believed science should benefit everyone, not enrich individuals. Despite growing influence, Faraday never forgot the importance of sharing knowledge with ordinary people. His commitment to education was one of the defining features of his career, and it played a major role in his global recognition. Faraday believed that science belonged to all, regardless of class or background, and he worked tirelessly to make scientific knowledge accessible. His Christmas lectures at the Royal Institution, which continue today, were designed to ignite young minds with curiosity and wonder. Faraday delivered these lectures with enthusiasm, using creative demonstrations to explain complex ideas in ways that anyone could understand. Thousands attended his talks, and newspapers often described the excitement they generated across London. This public engagement helped turn Faraday into a household name, admired not only by scientists, but also by the general public. What makes Faraday's rise even more extraordinary is that he achieved recognition at a time when social mobility was extremely limited. In the rigid class structure of Victorian England, people born into poverty rarely escaped it, but Faraday defied these expectations. His achievements challenged the belief that only the privileged could succeed in intellectual fields. As his fame spread across Europe and America, his story became a source of inspiration for countless young people who saw in him proof that knowledge could lift a person beyond the boundaries of their birth. Faraday became a symbol of possibility, demonstrating that education and curiosity were powerful tools for personal transformation. Faraday's relationship with mathematics is another important part of his rise. In an era when mathematics was becoming increasingly central to scientific work, Faraday's lack of formal training in the subject could have held him back. Yet he overcame this obstacle through sheer originality. He developed conceptual tools such as field lines, to describe physical phenomena that he could not express mathematically. These conceptual breakthroughs later allowed James Clerk Maxwell to formulate the equations of electromagnetism, solidifying Faraday's discoveries within the framework of modern physics. Maxwell himself famously said, "Faraday is, and must always remain, the father of that enlarged science of electromagnetism." It is remarkable that Faraday, without advanced education, created conceptual models so powerful that they became the foundation of electromagnetic theory. His success shows that deep understanding does not always depend on formal training. Faraday's intuition, developed through constant hands-on experimentation, gave him a unique ability to see patterns and relationships that others overlooked. His notebooks reveal endless sketches of loops, turns, and movement visualizations of forces that were invisible to the human eye. Through these drawings, Faraday reshaped the scientific understanding of electricity and magnetism, breaking away from the mechanical explanations that dominated his era. Another element of Faraday's rise was his remarkable memory and mental clarity. Though largely self-taught, he possessed a strong capacity to retain and organize information. When conducting experiments, he maintained detailed notes, recording not only the procedures and results, but also the reasoning behind each step. This rigorous documentation allowed him to track patterns, revisit earlier experiments, and build upon previous work systematically. Over the course of his career, Faraday filled thousands of pages with observations, diagrams, and reflections. These notebooks, now preserved in archives, are considered among the most important scientific manuscripts in history, offering insight into the mind of a genius who learned through practice rather than formal schooling. As Faraday continued to grow in recognition, he faced numerous challenges that tested his determination. One of the most significant obstacles was his health. In the 1840s, Faraday suffered a mental and physical breakdown, likely due to overwork and exposure to chemical fumes. For a period, he was forced to step back from scientific research, and many feared that his career had ended. Yet Faraday, true to his resilient nature, eventually recovered enough to return to experimentation. Although he never regained his full strength, his later years still produced important discoveries, including his work on magneto-optics and diamagnetism. Faraday's response to adversity demonstrated his profound inner strength. Rather than letting illness define him, he focused on what he could still achieve. Even when he could no longer remember complex details or work for long hours, his passion for science remained intact. His perseverance in the face of difficulty added to his reputation, revealing not only his brilliance but also his humanity. By the time Faraday reached the height of his career, he had become a respected figure across Europe. Scientists, philosophers, and political leaders regarded him as one of the greatest minds of the age. Honors and awards were offered to him from all directions, including invitations to join prestigious societies and universities. One of the most notable honors was the offer of knighthood from Queen Victoria. Faraday declined it politely, saying he preferred to remain simply Mr. Faraday. This decision reinforced the public's admiration for him, as it revealed his refusal to let status overshadow substance. Another honor he declined was burial in Westminster Abbey, instead choosing a simple grave near his home, reflecting his lifelong values of modesty and simplicity. Faraday's global recognition was not the result of self-promotion. Rather, it emerged naturally from the impact of his discoveries. His work changed the trajectory of modern civilization. It influenced communication, transportation, energy, engineering, and nearly every aspect of technological development. Without Faraday, the electrical age as we know it would not exist. Telephones, generators, electric motors, radio waves, and countless modern conveniences all trace their origins to his experiments. This profound influence earned him the title, the father of electricity and magnetism, a name he never claimed for himself, but one the world bestowed upon him. Faraday's influence extended beyond his lifetime through the work of scientists who built upon his discoveries. Maxwell's equations, which combined Faraday's insights into a coherent mathematical framework, paved the way for Einstein's theory of relativity and the entire field of modern physics. The chain of influence from Faraday to Maxwell to Einstein illustrates how one self-taught scientist's imagination reshaped the world. It is a powerful reminder that innovation often begins with individuals who think differently, who question assumptions, and who are willing to explore ideas with courage and curiosity. Today, Faraday's legacy continues to inspire scientists, engineers, educators, and students around the globe. His rise from poverty represents the triumph of human potential over social limitations. His achievements are celebrated not only for their scientific value, but for the values they symbolize: curiosity, perseverance, humility, and the belief that knowledge should be accessible to all. Faraday's life challenges the idea that genius is limited to elite institutions or privileged backgrounds. Instead, it reveals that great minds can emerge anywhere, provided they are given the space to grow and the encouragement to explore. Reflecting on Faraday's journey, it becomes clear that his success was rooted in more than talent. It came from a lifelong commitment to learning, an unshakable belief in the power of discovery, and a humble heart that never lost touch with its origins. Faraday's rise from a poor child in London to one of the most celebrated scientists in history is not just a story of scientific achievement. It is a story about the strength of the human spirit. It is about what becomes possible when someone refuses to accept the limitations of their circumstances and instead chooses to pursue knowledge with passion, persistence, and integrity. Faraday remains a symbol of what humanity can achieve when curiosity is allowed to flourish, when education is valued, and when individuals believe in the transformative power of learning. His legacy is a reminder that greatness is not about where one begins, but about the journey one undertakes. In every sense, Michael Faraday's rise from poverty to global recognition stands as one of the most inspiring scientific biographies ever told, a story that will continue to motivate future generations to question, explore, and discover. Michael Faraday's discovery of electromagnetic induction stands as one of the most transformative achievements in the history of science. It is the discovery that made modern electricity possible, the discovery that allowed humanity to move from simple static electrical experiments into an era powered by vast electrical networks. Faraday's work not only uncovered a hidden law of nature, but became the foundation for every generator, transformer, and electrical power system in use today. To understand the enormity of this discovery, one must step back into the early 19th century, a time when electricity was known mostly as a scientific curiosity. Before Faraday, electricity existed in laboratories as sparks, shocks, and small devices driven by chemical cells. No one had ever figured out how to produce electricity in a continuous, powerful, and practical form that could be used for machines, industry, and eventually entire cities. Many believed such a feat was impossible, but Faraday, with his extraordinary intuition and experimental skill, was determined to uncover the deeper relationship between electricity and magnetism. Faraday's path toward electromagnetic induction began long before his famous experiment of 1831. It grew out of years of curiosity, careful observation, and persistent questioning. In 1820, the Danish scientist Hans Christian Ørsted discovered that an electric current could deflect a magnetic needle. This simple observation shattered the long-standing belief that electricity and magnetism were unrelated forces. It was a revolutionary idea, and it immediately captured Faraday's attention. While many scientists were impressed by Ørsted's discovery, few pursued it with the same determination as Faraday. To Faraday, Ørsted had cracked open a door, one that might lead to an entirely new understanding of nature. If electricity could influence magnetism, he wondered whether magnetism could also generate electricity. This question became a driving motivation behind Faraday's research. The scientific community of the time believed that such a reversal might be possible, but no one had demonstrated it. Many researchers attempted to create electricity from magnetism, but they all failed. Their failures reinforced the assumption that magnetic forces could not create electrical ones. Faraday, however, did not give up. His unique ability to visualize invisible forces allowed him to approach the problem from a completely different angle. Rather than thinking of electricity and magnetism as substances or particles, he imagined them as fields, regions of influence surrounding magnets and electric currents. At a time when most scientists relied heavily on mathematics to express theories, Faraday used physical intuition and direct experimentation. This gave him the ability to see patterns others could not. Faraday's breakthrough came from a deceptively simple realization. Electricity might not be generated by a static magnetic field, but by a changing one. This insight transformed the entire investigation. All earlier experiments had tried to generate electricity simply by placing wires near strong magnets. These efforts produced no result. Faraday, however, began to think in terms of motion and change. He reasoned that if a magnetic field could influence a current, perhaps a shifting magnetic field could influence an electric charge enough to create motion, thus producing electricity. This was a subtle but revolutionary idea. It meant that the key to generating electricity was not magnetism alone, but magnetism in motion. In 1831, after years of thinking, sketching, and performing smaller trial experiments, Faraday finally conducted the series of tests that changed the world. He wrapped 2 coils of wire around an iron ring, one coil connected to a battery and the other connected to a galvanometer, an instrument for detecting electric current. Faraday then supplied current to the first coil and noticed something extraordinary. At the moment he connected the battery, the galvanometer on the second coil moved. When he disconnected it, the galvanometer moved again, but during the time the current was steady, the galvanometer showed nothing. This momentary current in the second coil was the critical clue Faraday needed. It confirmed that a changing magnetic environment, not a constant one, induces electricity. This experiment, often called the iron ring experiment, was the first clear demonstration of electromagnetic induction. With this single finding, Faraday had discovered a new law of nature. A changing magnetic field produces an electric current. This principle became known as Faraday's law of induction, and it forms the foundation for virtually every modern electrical device. But Faraday did not stop there. He continued experimenting relentlessly, trying to find more practical ways to generate continuous electrical currents. This led to another historic moment. Faraday built the first electrical generator by rotating a copper disc between the poles of a magnet. As the disc rotated, It cut across magnetic field lines, producing a steady flow of electrical current. This device, known as the Faraday disk or homopolar generator, was the ancestor of every generator and dynamo used in the modern world. Although the first generator produced a small amount of electricity, the principle behind it was astonishingly powerful. The idea that mechanical motion, such as turning a wheel, spinning a disk, or rotating a coil, could produce electricity fundamentally transformed human industry. Suddenly, electricity could be generated not only from chemical batteries, but from motion itself. This discovery laid the groundwork for power plants, which convert mechanical energy from steam turbines, water turbines, gas engines, or wind into electrical energy through electromagnetic induction. Every rotating generator on Earth, whether in a hydroelectric dam, a coal-fired plant, a wind turbine, or a nuclear plant, uses the same principle Faraday identified in 1831. Faraday's discovery of induction also made possible the invention of transformers, electric motors, induction coils, and countless other technologies. His work revealed that electricity and magnetism were not isolated phenomena, but part of a single system, electromagnetism. This insight allowed other scientists to build on his discoveries and ultimately led to the development of alternating current AC systems, which power most electrical grids today. Without Faraday's discovery, modern civilization would be unrecognizable. No factories powered by motors, no electric lights, no communication networks, no convenient transportation systems, and no digital world. The story of electromagnetic induction is, therefore, not just a scientific narrative, but a story that explains the entire foundation of technological progress. What makes Faraday's achievement even more extraordinary is the simplicity and clarity of his thinking. He approached the problem with an almost childlike curiosity, asking fundamental questions others overlooked. He was not content with observing effects. He wanted to understand causes. His notebooks reveal how he sketched magnetic fields as lines spreading out around magnets, looping and curving in space. These sketches were not mere drawings. They were visual models of invisible forces. They helped him understand how a conductor moving through magnetic lines could experience a push, a force on the charges inside it. This visualization eventually led to the idea that motion through a magnetic field pushes electrons, creating a current. This conceptual leap was far ahead of its time and paved the way for the modern field theory in physics. Faraday's discovery also reflects his incredible patience and discipline. Many experiments leading up to induction seemed to produce failures. But Faraday did not see them as failures. He saw them as stepping stones. Each experiment revealed something new, even if it was simply proof of what did not work. This methodical exploration allowed him to build a deep understanding of the relationship between electricity and magnetism. His success was a result of thousands of small insights, each one adding to his mental picture of how nature behaves. Faraday often spent long hours in the laboratory, adjusting wires, moving magnets, rewrapping coils, and repeating experiments with slight modifications. His ability to remain focused on a single problem for years demonstrated a rare combination of intellectual endurance and creative insight. Another key aspect of Faraday's discovery was his resistance to existing scientific prejudices. Many leading scientists of the time believed that electricity could only be produced through chemical reactions, such as those in batteries. They dismissed the possibility that magnetism could directly generate electricity. Faraday, however, trusted his observations more than established beliefs. This willingness to challenge accepted ideas was essential to his discovery. It allowed him to approach the problem with a fresh perspective, free from assumptions that limited others. This intellectual freedom was central to his success, and explains why Faraday was able to see opportunities where others saw impossibilities. Faraday's discovery of electromagnetic induction did not just revolutionize technology. It also transformed theoretical science. It provided crucial evidence that electricity and magnetism were deeply connected forces, paving the way for James Clerk Maxwell to create the equations that unified electromagnetism into a single theory. Maxwell's work, in turn, inspired the development of modern physics, influencing Albert Einstein and the emergence of relativity and quantum theory. Thus, Faraday's experiment with a coil of wire and a magnet initiated a chain of scientific progress that redefined our understanding of the universe. Faraday's discovery is also remarkable because it shows how powerful simple experiments can be. His apparatus coils of wire, magnets, iron rings were not expensive or complex. They did not require large laboratories or advanced equipment. Faraday relied on creativity, careful thinking, and deep curiosity rather than wealth or resources. This makes his discovery a powerful example of how scientific breakthroughs can arise from modest beginnings. Faraday's laboratory was filled with handmade tools, many of which he built himself. Yet it was in this simple environment that he uncovered a law of nature that powers an entire world. The significance of Faraday's discovery cannot be overstated. His work laid the foundation for industrialization, electrification, and the technological age. Without electromagnetic induction, we would live in a world without electrical power grids, without modern manufacturing, without electric transportation, without computers or smartphones. Every time a generator spins anywhere on Earth, whether powered by water, steam, wind, or nuclear reactions, it is Faraday's discovery that makes it work. His insight into the relationship between magnetic fields and electrical currents continues to drive innovation nearly 2 centuries later. Faraday's discovery of electromagnetic induction not only transformed the field of physics, but also redefined humanity's relationship with energy and technology. Before his experiments, electricity was largely an academic curiosity, confined to small laboratory demonstrations and electrochemical reactions. Scientists could produce sparks, shocks, and minor currents, but the concept of harnessing electricity on a large scale seemed out of reach. The world could not yet imagine a time when cities would glow at night with electric light, when factories would hum with electric machinery, or when communication would span continents in milliseconds. Faraday, through meticulous experimentation and extraordinary insight, provided the blueprint that made this world possible. The first critical element of Faraday's genius was his ability to think conceptually about forces that could not be seen. When most of his contemporaries were focused on tangible experiments measuring sparks, currents, or voltages, Faraday visualized invisible lines of force surrounding magnets. He imagined the way these lines curved, extended, and interacted with conductive materials. These mental images guided his experiments, allowing him to predict outcomes that others might never have considered. In doing so, Faraday demonstrated a rare cognitive skill, the ability to merge empirical observation with abstract reasoning. It was this combination that allowed him to conceive the very idea that motion through a magnetic field could induce electrical current. Faraday's insight challenged long-held assumptions in physics. At the time, many scholars believed that electricity and magnetism were entirely separate forces. The prevailing thought was that electricity was generated solely by chemical reactions, as in a battery, and that magnetism was a static property of certain materials. Faraday questioned these assumptions. He reasoned that if electricity could influence magnetism, as shown by Ørsted's discovery, then the converse might also be true. This kind of reasoning required both imagination and courage. To challenge scientific orthodoxy in the early 1800s was risky. Reputations could be ruined by pursuing ideas that seemed speculative or impossible. Yet Faraday, undeterred by social or professional pressures, allowed his curiosity to guide him. The experimental path to demonstrating induction was methodical and deliberate. Faraday did not achieve success immediately. He conducted countless preliminary tests, gradually refining his understanding of how magnetic fields could influence electrical currents. He experimented with different configurations of wires, magnets, coils, and iron cores. He observed subtle changes, recording even the slightest deflection in his galvanometer. Each of these experiments, even when producing minimal or unexpected results, contributed to a growing mental map of the underlying physical relationships. Faraday's process exemplifies a critical aspect of scientific discovery: perseverance. Success is rarely instantaneous. It emerges from the accumulation of careful observation, repeated testing, and incremental insight. The famous iron ring experiment of 1831 marked the culmination of this experimental process. In this setup, Faraday wrapped two separate coils of wire around a single iron ring. One coil was connected to a battery to create an electric current, and the other was attached to a galvanometer to detect any induced current. When Faraday connected or disconnected the battery, the galvanometer registered a brief current in the secondary coil. This observation was profound. It demonstrated unequivocally that a changing magnetic environment produces an electric current. Importantly, the current appeared only when the magnetic field changed, when the battery was connected or disconnected, not when the current was steady. Faraday had discovered a law of nature, one that governs the fundamental interaction between electricity and magnetism. Following this experiment, Faraday continued to explore practical applications of induction. He realized that continuous motion could produce continuous current, rather than just transient bursts. This insight led him to construct the first electrical generator, known as the Faraday disc. By rotating a copper disc between the poles of a magnet, he generated a steady flow of electrical current. While the device produced only a small amount of electricity, it was the first demonstration that mechanical motion could be converted directly into electrical energy. This principle underlies every electrical generator ever built, from the smallest laboratory dynamos to the massive turbines in modern power plants. Faraday had, in essence, unlocked a method for converting kinetic energy into usable electrical energy, a breakthrough that would eventually fuel the Industrial Revolution and the modern technological world. Faraday's experiments also revealed subtle but profound principles about the nature of electricity. He discovered that the magnitude of induced current depended on the speed of the magnetic change and the number of wire turns in a coil. These observations would later be formalized into the mathematical expression known as Faraday's law of electromagnetic induction. The law states that the induced electromotive force in a circuit is proportional to the rate of change of magnetic flux through the circuit. This relationship, elegantly simple yet universally applicable, governs the operation of transformers, generators, induction coils, and countless other electrical devices. Without it, modern electrical engineering would be impossible. The broader implications of Faraday's discovery extended beyond technology. It fundamentally altered humanity's understanding of natural forces. Before Faraday, electricity and magnetism were treated as isolated phenomena. His experiments demonstrated that they were interconnected, two aspects of a unified field of force. This insight laid the conceptual groundwork for James Clerk Maxwell's electromagnetic theory, which mathematically formalized the relationship between electric and magnetic fields. Maxwell's equations, in turn, became the foundation of modern physics, including radio waves, light, and quantum electrodynamics. Faraday's discovery was therefore not just a technological breakthrough. It was a cornerstone of scientific theory, a key to understanding the universe at a deeper level. One of the most remarkable aspects of Faraday's work is that he achieved all this without advanced mathematical training. Unlike many of his contemporaries, Faraday was largely self-taught in mathematics and relied primarily on physical intuition, visual reasoning, and hands-on experimentation. He conceived of lines of force, flux, and induction through observation and creative visualization. This ability to translate abstract physical phenomena into tangible experiments demonstrates the power of empirical thinking combined with imaginative reasoning. Faraday's work is often cited as evidence that groundbreaking scientific discovery does not always require formal education or sophisticated mathematics. It can also arise from persistent curiosity and disciplined experimentation. Faraday's approach to experimentation was meticulous and rigorous. He controlled variables carefully, repeated tests multiple times, and recorded observations with extraordinary precision. He also displayed immense creativity in designing apparatuses that could demonstrate subtle effects. Many of his instruments were handmade, crafted from available materials, yet they were ingenious in their function. This resourcefulness underscores the idea that innovation is not limited by resources, but by imagination and skill. Faraday's laboratory became a space where curiosity, discipline, and creativity converged, producing discoveries that would shape the future of human civilization. The practical consequences of electromagnetic induction are nearly impossible to overstate. Every power station, from small local plants to massive hydroelectric dams, relies on the principle Faraday discovered. Electric motors, transformers, and induction devices, all central to modern industry and technology, operate based on the interplay between magnetic fields and electric currents. Faraday's insight made it possible to transmit electricity over vast distances, to power machinery, and to develop communication systems such as telegraphs, telephones, and eventually radio. Every aspect of the electrical world we take for granted, light bulbs, computers, trains, medical imaging, and internet infrastructure, traces back to this fundamental discovery. Faraday's discovery also had profound economic and social implications. By making electricity accessible and practical, it fueled industrial growth, transformed urban environments, and improved quality of life. Factories became more efficient, cities became illuminated, and new industries emerged around electrical technology. The ability to generate and control electricity reshaped global economies and laid the groundwork for technological revolutions that continue today. In this sense, Faraday's discovery was not just scientific. It was transformative on a societal scale, shaping the modern world in every imaginable way. Moreover, Faraday's work exemplifies the principle that pure scientific inquiry can lead to practical innovations. He was not motivated primarily by profit or application. He was driven by curiosity and the desire to understand natural laws. Yet the fruits of his research proved immensely practical. This demonstrates the value of supporting fundamental science, even when immediate applications are not apparent. Faraday's experiments with coils and magnets, motivated by intellectual curiosity, ultimately enabled the global electrical infrastructure we rely on today. Finally, Faraday's discovery of electromagnetic induction underscores the human capacity for insight and creativity. It was not a single moment of luck, but the culmination of years of careful observation, persistent experimentation, and imaginative thinking. It required both a deep understanding of natural phenomena and the courage to challenge conventional assumptions. Faraday's work illustrates that discovery often emerges from the willingness to ask questions that others avoid, to explore paths that seem uncertain, and to persist through failure. It is a story of human ingenuity, perseverance, and vision, the kind of achievement that defines not just science, but civilization itself. Michael Faraday's work, establishing the deep connection between electricity and magnetism, represents one of the most revolutionary breakthroughs in the history of science. Before Faraday, electricity and magnetism were largely regarded as separate phenomena. Electricity was observed in experiments involving static charges, batteries, and simple circuits, while magnetism was understood mainly through the behavior of lodestones and permanent magnets. The scientific community had no clear idea that these two forces could be intimately related, let alone influence one another. Faraday, through meticulous experimentation, observation, and conceptual innovation, revealed that electricity and magnetism were not isolated phenomena, but interconnected aspects of a single underlying force. This insight laid the foundation for modern electromagnetism and enabled generations of scientists and engineers to develop technologies that power our world today. Faraday's first step toward understanding this connection came after the discovery of the effect of electricity on magnets by Hans Christian Ørsted in 120. Ørsted observed that a compass needle deflected when placed near a wire carrying an electric current. While this was the first clue that electricity and magnetism could interact, many scientists viewed it as an isolated phenomenon without deeper implications. Faraday, however, saw something far greater, a systematic relationship that could be studied, quantified, and eventually harnessed. Unlike others, he asked not just whether electricity could influence magnets, but whether the reverse could also be true. Could a magnetic field generate electricity? This question would ultimately lead to his discovery of electromagnetic induction. Faraday approached the problem with a combination of imagination and experimental rigor. He visualized forces as lines of influence, a conceptual tool that allowed him to see patterns where others could not. When a current passed through a wire, it created a magnetic field around it. When a magnet was moved near a conductor, the changing magnetic field could induce an electric current in the conductor. This realization, now formalized as Faraday's law of induction, demonstrated for the first time that electricity and magnetism are not independent forces, but interdependent. The motion of one could produce effects in the other, revealing a fundamental symmetry in nature that had previously been hidden. Faraday's experiments were elegantly simple but conceptually profound. He used coils of wire, magnets, and galvanometers to demonstrate that a changing magnetic field produces a current. In one experiment, he wrapped two coils of wire around a soft iron ring. By sending a current through one coil, he induced a current in the second coil, even though there was no direct electrical connection between them. This clearly showed that the magnetic field generated by electricity could, in turn, create electricity in a separate conductor. This mutual relationship established a clear and repeatable link between the two forces, moving the understanding of physics far beyond previous fragmented observations. In addition to demonstrating electromagnetic induction, Faraday explored other phenomena that further confirmed the relationship between electricity and magnetism. He investigated the effects of moving conductors in magnetic fields and showed that continuous motion could generate a continuous current. These experiments demonstrated that not only could electricity influence magnetism, but magnetism could produce electricity. Faraday's findings effectively unified two previously separate areas of study into a single field of electromagnetism. His careful observations revealed patterns and relationships that would eventually allow scientists to predict and manipulate electrical and magnetic forces in practical applications. One of Faraday's most enduring contributions was the conceptual framework he developed to describe these phenomena. He introduced the idea of lines of force, a visual representation of the invisible fields surrounding magnets and currents. This conceptual tool allowed him to reason about interactions between electricity and magnetism in ways that could be tested experimentally. Lines of force provided a model that was later formalized mathematically by James Clerk Maxwell, who built upon Faraday's insights to create the complete theory of electromagnetism. Faraday's lines of force were not mere illustrations. They were a powerful cognitive tool that bridged the gap between observation and theory, showing that electricity and magnetism are two aspects of the same natural law. The implications of Faraday's discovery were both scientific and technological. On the scientific side, his work showed that forces previously thought to be separate could interact systematically. This insight paved the way for Maxwell's equations, which mathematically unified electric and magnetic fields into one coherent framework. Maxwell's work, building directly on Faraday's concepts, demonstrated that light itself is an electromagnetic wave linking optics, electricity, and magnetism in a profound unification. Without Faraday's experiments and conceptual breakthroughs, such a unification would have been nearly impossible to achieve. On the technological side, Faraday's discovery made possible the generation, transmission, and utilization of electricity. Generators, transformers, electric motors, and countless other devices rely on the principle that electricity and magnetism are interrelated. By showing that a moving magnetic field can produce an electric current, Faraday provided the theoretical and experimental basis for harnessing electrical energy in practical forms. The electric grid, modern transportation systems, telecommunications, and industrial machinery all depend on this fundamental connection between electricity and magnetism. Faraday's work transformed electricity from a laboratory curiosity into a practical, universal resource. Faraday's discovery also illustrates the power of observation and experimentation in scientific progress. He achieved these insights without advanced mathematical training, relying instead on intuition, careful experimentation, and conceptual reasoning. He meticulously tested his ideas in the laboratory, using simple equipment such as magnets, coils, and galvanometers. The clarity and reproducibility of his experiments convinced the scientific community of the fundamental connection between electricity and magnetism. His approach demonstrated that deep scientific insight often arises from the ability to see patterns, ask the right questions, and persist in testing hypotheses, rather than from formal training or complex tools alone. The deep connection between electricity and magnetism that Faraday revealed also had philosophical implications. It suggested that natural forces are interconnected in ways that can be understood through careful observation and reasoning. This unified perspective encouraged scientists to look for underlying principles rather than isolated effects. Faraday's work exemplifies the transition from a descriptive, fragmented understanding of physical phenomena to a unified, law-based approach that underpins modern science. Faraday's influence extended far beyond his own experiments. He inspired generations of scientists, including James Clerk Maxwell, Heinrich Hertz, Nikola Tesla, and Albert Einstein. Maxwell built on Faraday's concept of lines of force to formulate the mathematical theory of electromagnetism. Hertz later demonstrated that electromagnetic waves propagate through space, confirming the theoretical predictions that arose from Faraday's work. Tesla applied the principles of electromagnetic induction to develop alternating current systems, revolutionizing electrical power distribution. Faraday's insight that electricity and magnetism are deeply connected served as the foundation for these groundbreaking advancements, and continues to inform contemporary research in physics and engineering. In summary, Michael Faraday's work established the deep connection between electricity and magnetism by demonstrating that a changing magnetic field induces an electric current, and that electric currents create magnetic fields. Through experiments with coils, magnets, and galvanometers, Faraday revealed that these two forces are interdependent, forming the basis of the unified field of electromagnetism. His conceptual innovations, including lines of force, allowed future scientists to model, predict, and harness these interactions in ways that transformed both science and technology. Faraday's discoveries turned electricity from a curiosity into a practical force capable of powering modern civilization, unified disparate areas of physics, and laid the groundwork for future generations to explore and expand the limits of human knowledge. Michael Faraday's contributions to electrochemistry, particularly his formulation of the laws of electrolysis, represent one of the most important intersections between theoretical science and practical application. Before Faraday, the nature of chemical reactions involving electricity was poorly understood. Scientists knew that certain reactions could be driven by electric currents, but there was no systematic framework to quantify these processes. Faraday's insight transformed this area of study by demonstrating that chemical change and electrical energy are fundamentally linked through precise quantitative laws. These laws, now known as Faraday's first and second laws of electrolysis, provided the foundation for modern electrochemistry and became critical for numerous industrial processes that rely on controlled chemical reactions. Faraday's first law of electrolysis states that the amount of chemical substance liberated at an electrode during electrolysis is directly proportional to the total electric charge passed through the substance. In simpler terms, the greater the flow of electric current, the greater the amount of material produced or consumed at the electrodes. This law was revolutionary because it established a clear, predictable relationship between electricity and chemical transformation. Prior to this discovery, chemical reactions driven by electricity were observed experimentally, but their results were often inconsistent and poorly understood. Faraday's law provided a mathematical framework, allowing scientists and engineers to calculate exactly how much of a substance would be produced or consumed for a given current and time. Faraday's second law of electrolysis goes even further, connecting the amounts of different substances liberated by the same quantity of electricity. It states that the masses of substances liberated or dissolved by the same quantity of electricity are proportional to their equivalent weights. This means that each element requires a specific, predictable amount of electric charge to undergo a chemical change. For example, the electrolysis of water produces hydrogen and oxygen in precise proportions, and electroplating metals or refining metals like copper, silver, and aluminum relies on this same principle. By demonstrating that these quantities are predictable, Faraday provided the basis for standardization in chemical processes and industrial applications. The impact of Faraday's laws on modern chemistry cannot be overstated. Electrochemistry became a quantitative science, moving beyond mere observation to predictable and reproducible experimentation. Scientists could now measure the electric charge needed to drive reactions, understand the behavior of ions in solution, and develop precise techniques for manipulating chemical transformations. Faraday's work clarified the relationship between atoms, ions, and electrons, providing one of the earliest experimental confirmations of the concept of atomic structure and the role of electric charge in chemical reactions. This understanding influenced later developments in chemistry, including the study of reaction mechanisms, ionic compounds, and the emerging field of physical chemistry. Industrial applications of Faraday's laws were almost immediate and transformative. Electroplating, the process of coating one metal with another using electricity, became highly predictable and efficient because the amount of deposited metal could now be calculated. Industries that required precise coatings for tools, jewelry, and machinery benefited directly from Faraday's insights. Similarly, the electrolytic refining of metals, such as copper and aluminum, was made much more efficient and reliable. These processes not only improved product quality, but also reduced waste and costs. Faraday's laws allowed engineers to design processes that used electricity optimally, preventing overuse or underuse of power and ensuring consistent chemical production. Beyond metal refining and electroplating, Faraday's work laid the groundwork for emerging industries that rely on electrochemical principles. The production of chlorine, sodium hydroxide, and other chemicals through the electrolysis of salts became possible with precise control, enabling the mass production of essential materials, manufacturing, sanitation, and agriculture. Electrolysis also became critical in energy storage technologies. Batteries and fuel cells, which rely on reversible electrochemical reactions, are direct applications of Faraday's principles. By understanding how much material is transformed per unit of electricity, engineers and chemists could optimize energy storage systems for efficiency and durability. Even today, modern lithium-ion batteries, hydrogen fuel cells, and electrolysis-based hydrogen production trace their operational principles back to Faraday's foundational work. Faraday's laws also influenced scientific understanding of the behavior of ions in solutions. His experiments demonstrated that ions carry electrical charge and move predictably under the influence of an electric field. This led to the concept of cations and anions and provided a concrete explanation for how chemical substances are transformed during electrolysis. By linking electrical charge to chemical quantity, Faraday essentially quantified the connection between matter and energy, providing a deeper understanding of the fundamental principles that govern chemical reactions. His work bridged physics and chemistry, showing that electrical forces are not just abstract phenomena, but are intimately involved in the transformation of matter. One of the reasons Faraday's laws were so powerful is their simplicity and universality. They apply to all electrolytic processes, regardless of the chemical substance involved. This universality made Faraday's laws a foundational tool in both theoretical and applied chemistry. Chemists could use the laws to predict reaction outcomes, calculate material requirements, and ensure consistency in experimental and industrial settings. Faraday's work provided a level of precision and predictability previously unavailable, transforming the practice of chemistry from qualitative observation to quantitative science. The educational impact of Faraday's discoveries was also profound. Students and researchers learned that electricity could be used to control chemical reactions in predictable ways, opening up new possibilities for experimentation and innovation. Faraday's approach, combining careful observation, meticulous measurement, and theoretical reasoning, became a model for scientific investigation. His work demonstrated the value of connecting theory and practice, showing that deep understanding of natural laws could lead directly to practical applications. This philosophy continues to guide research in chemistry, materials science, and engineering. Faraday's influence extended beyond chemistry to fields such as metallurgy, energy production, and environmental science. Electrochemical refining improved the purity of metals, critical for electronics, aerospace, and medical industries. Electrolysis of water enabled the production of hydrogen as a clean fuel. Electrochemical methods for extracting and purifying chemicals became key components of industrial chemistry. In every case, the ability to predict and control chemical reactions using electrical charge, directly derived from Faraday's laws, made these processes practical and economically viable. In conclusion, Faraday's laws of electrolysis established a precise quantitative relationship between electricity and chemical change, revolutionizing both modern chemistry and industrial processes. By demonstrating that the amount of material transformed is proportional to the electrical charge and depends on the chemical properties of the substance, Faraday provided a foundation for predictable, reproducible, and efficient chemical reactions. His work transformed electrochemistry into a rigorous scientific discipline, enabled technological innovations such as electroplating and metal refining, and laid the groundwork for modern energy, storage, and chemical manufacturing. Faraday's insights exemplify the powerful interplay between fundamental science and practical application, demonstrating that careful observation, creative experimentation, and theoretical insight can reshape both our understanding of the natural world and the tools we use to navigate it. His contributions continue to influence chemistry, engineering, and industry, making Faraday's laws of electrolysis an enduring legacy of scientific genius. Michael Faraday's invention of the Faraday cage stands as a testament to his visionary understanding of electricity and its interaction with matter. While much of Faraday's fame comes from his discoveries in electromagnetism and electrochemistry, the Faraday cage represents a direct, practical application of his insights into how electric charges behave in conductive materials. The Faraday cage, a structure designed to shield its interior from external electric fields, continues to have profound applications in science, engineering, and everyday life. Its invention demonstrates Faraday's remarkable ability to transform abstract principles into practical innovations that safeguard both people and technology. The idea behind the Faraday cage is deceptively simple yet profoundly effective. Faraday discovered that when an external electric field is applied to a conductor, the charges within the conductor redistribute themselves in such a way that the field's effects are neutralized inside the enclosure. In other words, the conductive material acts as a shield, preventing the electric field from penetrating and protecting whatever is inside. Faraday demonstrated this phenomenon in the early 1830s through careful experiments, using metal screens and cages to show that delicate electrical instruments placed inside remained unaffected by external electrical discharges. This empirical demonstration provided tangible proof of a concept that was previously theoretical, bridging the gap between abstract electricity studies and practical engineering solutions. Faraday's experiments with cages were elegant and insightful. He placed an electroscope, a device used to detect electric charge, inside a metal enclosure, and then applied strong electrical charges to the outside. Despite the intensity of the electrical activity surrounding the cage, the electroscope inside remained completely unaffected. This clearly demonstrated that the electric field had been entirely blocked from penetrating the enclosure. Faraday's meticulous documentation of these experiments showed not only the phenomenon itself, but also the reproducibility of the results, which is a hallmark of rigorous scientific methodology. Through these experiments, Faraday established that electric fields act on the outer surface of a conductor, leaving the interior shielded, a principle that is the foundation of the Faraday cage. The Faraday cage has numerous practical applications, both in Faraday's time and today. One of the earliest applications was in protecting sensitive electrical equipment from accidental electrical discharges, such as sparks and static electricity. Laboratories, telegraph systems, and other early electrical installations were particularly vulnerable to disruptions caused by stray electric currents. By enclosing equipment in metal cages or screens, engineers could ensure consistent operation and prevent damage. Faraday's insight thus immediately bridged theoretical knowledge and practical problem solving, demonstrating the value of applied science. Over time, the Faraday cage has been adapted and expanded into countless modern applications. Perhaps the most widely recognized is its use in protecting people and equipment from lightning strikes. Lightning carries massive electrical currents, and buildings or vehicles designed with conductive enclosures, effectively acting as Faraday cages, can safely redirect these currents around occupants or sensitive electronics. For instance, a car in a thunderstorm functions as a Faraday cage. The metal frame channels the lightning around the passengers, leaving them unharmed. Similarly, lightning protection systems in buildings often employ conductive paths and grounded enclosures to shield inhabitants and equipment from potentially catastrophic electric surges. In addition to lightning protection, Faraday cages play a critical role in modern electronics and telecommunications. Sensitive instruments such as oscilloscopes, signal analyzers, and laboratory measurement devices require isolation from external electromagnetic interference, EMI, to function accurately. Faraday cages provide this isolation, ensuring that electrical noise from nearby equipment, power lines, or radio signals does not interfere with precise measurements. Without such shielding, modern research and industrial processes relying on sensitive instrumentation would be severely compromised. Faraday's invention thus continues to support the advancement of science by enabling accurate experimentation and data collection in controlled conditions. Another significant application of Faraday cages is in the protection of digital data and communication systems. Electromagnetic pulses EMPs, whether from natural sources like solar flares or man-made sources like high-altitude nuclear detonations, can generate intense electric fields capable of damaging electronics. Faraday cages, when properly designed, can protect computers, servers, and other critical systems from these potentially catastrophic effects. In this sense, Faraday's invention has not only practical industrial and laboratory applications, but also national security and disaster preparedness relevance. Governments, military installations, and critical infrastructure facilities employ Faraday shielding to ensure resilience against electromagnetic threats. The Faraday cage also finds applications in everyday consumer products. Microwave ovens, for example, are enclosed in a conductive mesh that prevents microwaves from escaping while allowing users to safely heat food. Even the small perforations in the oven door act as a Faraday shield, keeping high-frequency radiation contained within the appliance. This is a direct application of Faraday's principle, demonstrating how fundamental scientific discoveries can seamlessly translate into practical, everyday benefits for society. Similarly, some high-end audio equipment, mobile devices, and laboratories use miniaturized Faraday enclosures to minimize interference and ensure optimal performance. The principle behind the Faraday cage is also fundamental to scientific research into electromagnetic waves and radiation. Scientists conducting experiments on radio, frequency communication, wireless technology, and electromagnetic compatibility often use Faraday cages to isolate their experiments from background interference. By controlling the environment, researchers can achieve more accurate and reproducible results, accelerating technological development. Faraday's discovery has thus become a cornerstone of experimental methodology in modern physics, electrical engineering, and communication sciences. The theoretical implications of the Faraday cage were as significant as the practical ones. Faraday's experiments demonstrated that electric charges do not exist in isolation, but interact with the surrounding environment in predictable ways. The redistribution of charge along the surface of a conductor to neutralize an external electric field revealed a deeper understanding of the behavior of electric fields and equipotential surfaces. This insight influenced later developments in electrostatics, electromagnetic theory, and even quantum electrodynamics. James Clerk Maxwell, building on Faraday's experimental work, formalized the equations of electromagnetism that describe how electric and magnetic fields propagate and interact. Without Faraday's initial insight into shielding and field behavior, much of this theoretical development would have lacked empirical grounding. Faraday's invention is also a testament to his creative approach to science. He was able to take abstract principles, such as the behavior of electric charges in a conductor, and design experiments that made these principles tangible and understandable. The Faraday cage exemplifies how experimental ingenuity can lead to practical solutions that have long-lasting societal impact. Unlike many inventions that emerge from trial and error or incremental improvement, the Faraday cage arose directly from a deep understanding of the fundamental laws of nature, highlighting Faraday's unique ability to translate theory into innovation. In conclusion, the Faraday cage is a groundbreaking invention that remains as relevant today as it was when Faraday first demonstrated its principles. By showing that a conductive enclosure can shield its interior from external electric fields, Faraday provided a tool with countless applications, from lightning protection and laboratory shielding to digital security and microwave ovens. The Faraday cage embodies the essence of applied science, a principle derived from careful observation and experimentation that produces tangible, real-world benefits. Faraday's work in this area exemplifies his ability to blend theoretical insight with practical utility, cementing his legacy not only as a pioneer of electromagnetism, but also as an innovator whose discoveries continue to protect, enable, and enhance modern life. Michael Faraday was not only one of the most brilliant experimental scientists of his era, but also one of the most effective and influential science communicators in history. Beyond his groundbreaking discoveries in electricity, magnetism, and electrochemistry, Faraday's public lectures played a transformative role in cultivating scientific curiosity and fostering a culture of inquiry among students, scholars, and the general public. At a time when formal scientific education was limited and access to cutting-edge research was restricted, Faraday brought science directly to people, demonstrating that it could be both understandable and inspiring. Through his lectures, he bridged the gap between complex scientific concepts and accessible knowledge, leaving a lasting legacy on education, popular science, and intellectual engagement. Faraday's approach to public lectures was deeply rooted in his belief that science should be shared, not hoarded. He saw knowledge as a public good and believed that learning should be experiential and engaging. His lectures were carefully designed to illustrate scientific principles through vivid demonstrations rather than abstract theory alone. For instance, in his famous Christmas lectures at the Royal Institution, Faraday presented experiments involving electricity, magnetism, chemical reactions, and light. These demonstrations were visually striking. Glowing discharges, moving magnets, chemical color changes, and sparking circuits captured the imagination of his audience and made otherwise invisible forces tangible. Faraday's ability to transform abstract phenomena into observable events made complex scientific ideas accessible to audiences of all ages and educational backgrounds. The impact of Faraday's lectures was both immediate and long-lasting. Students, apprentices, and members of the public who attended his presentations were not merely passive spectators. They were participants in a process of discovery. Faraday often encouraged curiosity, questioning, and experimentation, showing that scientific understanding could be built through observation and reasoning. By demonstrating that even fundamental forces like electricity and magnetism could be studied with relatively simple apparatuses, he inspired a sense of possibility. His lectures often included small experiments that audiences could attempt themselves, fostering hands-on learning long before it became a standard pedagogical method. This approach not only helped people understand scientific principles, but also instilled a sense of confidence that they could explore and experiment independently. Faraday's lectures were particularly influential in shaping the scientific education of younger generations. Many students who attended his demonstrations went on to become scientists, engineers, and educators themselves, carrying forward his methods and insights. His emphasis on observation, careful experimentation, and clear communication became a model for teaching science, showing that complex concepts could be conveyed without relying solely on mathematical formalism. For many young scholars, Faraday's lectures were an introduction to the scientific method itself, emphasizing curiosity, patience, and disciplined inquiry. They illustrated that science was not an exclusive domain of the wealthy or highly educated, but could be pursued by anyone willing to observe, ask questions, and explore. The Royal Institution Christmas lectures, which Faraday delivered for over a decade, are perhaps the most enduring example of his public impact. These lectures were aimed at young people and designed to be both educational and entertaining. Faraday often structured them around a central theme, such as electricity or chemistry, and demonstrated principles step by step, gradually building understanding. The lectures combined visual demonstrations, clear explanations, and engaging storytelling, creating a sense of wonder and excitement. They were so influential that they established a tradition that continues today, with thousands of students attending each year and many more accessing the lectures through publications and broadcasts. In this way, Faraday institutionalized the practice of public scientific education, ensuring that his influence extended far beyond his immediate audience. Faraday's communication style was characterized by clarity, humility, and enthusiasm. He avoided overly technical language whenever possible, instead using analogies and visual demonstrations to convey ideas. For example, he might illustrate the concept of a magnetic field with iron filings, or show the behavior of gases through colorful chemical reactions. By focusing on observation and understanding rather than memorization, he helped audiences internalize scientific principles in a way that felt intuitive and engaging. Faraday's enthusiasm was contagious. His genuine excitement about discovery inspired students and scholars alike to pursue their own questions and experiments. Many accounts from his contemporaries describe audiences being captivated by his energy, curiosity, and ability to make invisible forces visible. Faraday's lectures also emphasized the interconnectedness of scientific phenomena, showing that discoveries in one area often had implications for others. He would link chemical reactions to electrical phenomena or magnetism to mechanical motion, highlighting the unity and coherence of natural laws. This approach encouraged a holistic understanding of science, rather than compartmentalized knowledge. For students and scholars, this perspective fostered critical thinking and creativity, as they were encouraged to make connections between seemingly unrelated observations. Faraday's lectures thus cultivated not only curiosity, but also the analytical and integrative skills necessary for scientific innovation. The influence of Faraday's lectures extended internationally. His clear demonstrations, rigorous methods, and communicative style were widely admired and emulated by scientists and educators around the world. Publications of his lecture, notes, and experiments were circulated widely, allowing those who could not attend in person to benefit from his teaching. Faraday's approach influenced the development of science education in Europe and beyond, demonstrating that public engagement with scientific knowledge was both possible and valuable. In an era before mass media, Faraday's lectures played a key role in democratizing access to scientific ideas, showing that knowledge could inspire curiosity across social and educational boundaries. Faraday's commitment to public education was not limited to formal lectures. He mentored young students, apprentices, and assistants in the laboratory, emphasizing hands-on learning and careful observation. He encouraged them to experiment, make mistakes, and learn from results, instilling the values of scientific rigor and intellectual curiosity. Many of these students went on to make significant contributions themselves, perpetuating Faraday's influence. His dedication to nurturing the next generation of scientists ensured that his impact would persist far beyond his own lifetime, shaping the culture of scientific inquiry for decades. In conclusion, Michael Faraday's public lectures were a transformative force in promoting scientific curiosity and education. Through clear explanations, engaging demonstrations, and an emphasis on observation and experimentation, he inspired generations of students, scholars, and the general public. Faraday made science accessible, exciting, and meaningful, bridging the gap between abstract principles and practical understanding. His influence extended beyond individual lectures, shaping science education, mentoring young scientists, and establishing traditions of public engagement that continue to this day. Faraday's ability to communicate the wonder and rigor of science demonstrates that the power of knowledge is not only in discovery, but in the ability to inspire others to explore, question, and understand the natural world. Michael Faraday's discoveries in electromagnetism and electrochemistry have had a profound and lasting impact on the development of modern electrical power and technology. While Faraday conducted his groundbreaking experiments in the early 19th century, long before the widespread industrial use of electricity, the principles he uncovered continue to underpin nearly every aspect of contemporary electrical systems. His work on electromagnetic induction, the relationship between electricity and magnetism, and the principles of electrochemistry laid the theoretical and practical foundation for the generation, transmission, and utilization of electric power. Without Faraday's contributions, the modern world as we know it illuminated cities, powered transportation, advanced communications, and digital technology would not exist. Faraday's discovery of electromagnetic induction in 1831 is perhaps his most significant contribution to modern electrical technology. Through careful experimentation, he demonstrated that a changing magnetic field could induce an electric current in a conductor. This principle is the core concept behind all electric generators, which convert mechanical energy into electrical energy. Faraday's simple yet elegant experiments, such as moving a magnet through a coil of wire or using an iron ring with multiple coils, showed that electricity could be generated by motion rather than relying solely on chemical reactions in batteries. This insight enabled engineers and inventors to design practical devices capable of producing electricity on a large scale, forming the foundation of power generation for homes, factories, and cities. Electric generators, which power virtually all modern electrical grids, rely directly on Faraday's principle of electromagnetic induction. Whether a generator is driven by a hydroelectric turbine, a steam engine, a wind turbine, or a gas-powered motor, the basic mechanism remains the same. Conductors move through a magnetic field to produce a current. Faraday's discovery provided the theoretical understanding necessary to design these machines, allowing engineers to calculate the optimal number of wire turns, the strength of the magnetic field, and the rate of motion required to generate electricity efficiently. Modern power plants, from massive dams to nuclear facilities, operate using the very principle Faraday uncovered, demonstrating the enduring relevance of his work. Faraday's understanding of the relationship between electricity and magnetism also made possible the development of electric motors. Just as a moving magnetic field can generate electricity, an electric current in a magnetic field produces mechanical motion. This reciprocity underpins the operation of electric motors, which convert electrical energy into mechanical energy. Electric motors power countless devices today, from household appliances and industrial machines to electric vehicles and robotics. The technological revolution driven by motors, industrial automation, electrified transportation, and smart devices traces its roots directly to Faraday's discoveries. By revealing the connection between electric currents and magnetic forces, Faraday provided the foundation for engineers to harness energy in entirely new ways. Faraday's work on electrochemistry further supports modern electrical technology. His laws of electrolysis, which quantify the relationship between electric charge and chemical change, enabled precise control of electrochemical processes. These principles are critical in the production of batteries, which store and release electrical energy in a controlled manner. Modern rechargeable batteries, from lithium-ion to lead-acid systems, rely on the predictable movement of ions and electrons, a concept Faraday formalized through his experiments. Without understanding how electricity interacts with chemical substances, reliable energy storage and portable electrical devices would not be possible. Faraday's work essentially made energy transport and storage feasible on both small and large scales. Faraday's invention of the Faraday cage, which shields sensitive electronics from external electrical interference, is another example of his discoveries underpinning modern technology. Electrical systems today are highly sensitive to electromagnetic interference, which can disrupt communications, computing, and instrumentation. By demonstrating that conductive enclosures can block electric fields, Faraday provided a principle that engineers now use to protect devices ranging from computers and medical instruments to telecommunications, equipment, and laboratory apparatus. In essence, Faraday's work ensures that electrical and electronic systems can operate safely, reliably, and efficiently in environments filled with potential interference. The broader influence of Faraday's discoveries extends to the entire electrical grid and energy infrastructure. Transmission lines, transformers, and substations, all of which enable the delivery of electricity over long distances, depend on principles of electromagnetism and induction. Transformers, which increase or decrease voltage for efficient transmission, operate on the principle of a changing magnetic field inducing a current in a secondary coil, directly applying Faraday's law. The ability to transmit electricity from power plants to homes and businesses, safely and efficiently, is a direct consequence of the theoretical foundation Faraday established nearly 2 centuries ago. Every watt of electricity flowing through modern grids is a testament to his pioneering work. Faraday's contributions also paved the way for the electronics revolution. Semiconductors, transistors, integrated circuits, and microprocessors all rely on controlled movement of electrons and understanding of electromagnetic principles. Even wireless communication technologies, such as radio, television, and modern cellular networks, depend on electromagnetic waves, which Faraday's experiments helped to conceptualize. His visualization of lines of force around magnets and currents inspired James Clerk Maxwell to develop the mathematical theory of electromagnetism, which later enabled the generation, propagation, and reception of electromagnetic waves. Without Faraday, the theoretical framework for radio, radar, and Wi-Fi would not exist. Moreover, Faraday's discoveries fostered a culture of innovation and experimentation that has driven technological progress ever since. His meticulous experimentation, creative problem-solving, and insistence on understanding natural phenomena through observation set a standard for engineers and scientists. Every advancement in electrical engineering, power generation, electronics, and even renewable energy can trace a conceptual lineage back to Faraday's laboratory. His influence is not limited to individual inventions. It underpins the methodology and principles that govern the design and operation of modern electrical technology. Finally, Faraday's discoveries continue to inspire emerging technologies. Renewable energy systems, including solar, wind, and tidal power, all rely on principles of electromagnetic induction for converting energy into electricity. Electric vehicles, smart grids, and energy storage solutions operate using concepts Faraday first demonstrated. Even cutting-edge research in quantum, electronics, and superconductivity builds on the fundamental understanding of electricity and magnetism that Faraday helped establish. In this sense, Faraday's work forms the backbone not only of existing technology, but also of the innovations that will define the future of energy and electrical systems. In conclusion, Michael Faraday's discoveries form the backbone of modern electrical power and technology by establishing the principles that govern the generation, transmission, and utilization of electricity. His work on electromagnetic induction enabled the creation of generators and transformers. His insights into electricity and magnetism made electric motors possible. His laws of electrolysis advanced energy storage and battery technology, and his invention of the Faraday cage ensures the safe operation of electrical systems. Beyond these direct applications, Faraday's conceptual innovations and experimental methods laid the foundation for the electronics, communications, and renewable energy technologies that define contemporary life. Every aspect of modern electrical power and technology, from homes and industry to transportation and digital communications, rests upon the principles Faraday uncovered, confirming his role as one of the most important scientific figures in history.